Hi, my name is Afreen Bhumgara, and today I'm going to be presenting my project for EE432 Advanced Computer Vision. So my topic is Texture Image Analysis and Classification Methods, a survey. So let's get into it. So what is texture? So while there is no formal definition of texture, researchers define texture as a regional image property, and they characterize it as a repeating pattern or combination of the variations in the image intensity levels between the neighborhood pixels. So texture diagnosis in a human vision system or for humans, it's feasible, but in machine vision or computer vision domains, it's a really complex and challenging task. And that is why if we have some computational efficiency, that's a plus. So this is a human vision based machine perception task. And image texture can be categorized into fine texture, coarse texture, grain texture, or smooth. This depends on the texture primitive. So these texels or texture elements characterize the image texture properties. So in this image over here, you can see that the above like three textures, they are composed of lines of the same length and same intensities, but they have different textures. So this shows us the visibility of texture distinctions. So what is texture analysis? With texture analysis, we aim for the precise detection and segmentation of a certain region of interest or ROI. And this is used to partition the images into ROIs and to classify those ROIs. So with this, we can provide descriptors to categorize the textural images. And here we assign an unknown sample ROI to a predefined category, label, or class if we are doing supervised texture classification. And there has been extensive research on texture analysis that has taken place over the past 30 years in the computer vision and the pattern recognition community. So talking about the applications of texture analysis, it has a lot of applications, and that's why it's been a really researched field. So texture analysis can help with the segmentation of satellite and aerial imagery, object tracking, pattern recognition, even content-based image retrieval in biometrics like face detection, fingerprint recognition, for defect detection, image analysis, remote sensing. So it has a wide range of applications in the computer vision domain. And now going on to the primary issues in texture analysis. So here you can see in the first image and image A, we have five different textured regions. In image B, we are now classifying those different textured regions into different like category labels. And we may know the category labels beforehand if you're doing like supervised classification, or we may not have a prior knowledge about the labels. And in the third image, you can see that we're performing texture segmentation to detect the boundaries. So these are actually the four major issues in texture analysis, which is texture classification, segmentation, synthesis, and shape extraction. So in texture classification, we take a unique like ROI. We detect the texture in the ROI, find out the unique characteristics and extract that. And then we classify which texture, like which set of classes does the texture belong to. So we assign the textured region to a predetermined set of class. And some statistical methods used here are contrast, entropy, GLCM. In texture segmentation, we identify the boundaries between the textured regions in the image. And in texture synthesis, we actually construct large digital images from small images using structural content. And texture shape extraction, here we extract the textural shapes like through 3D surface geometry. And we also sometimes like transform the texture shapes, like we transform them from 2 dimensions to 3 dimensions. So that takes place in shape extraction. So these are the primary issues that texture analysis deals with, and texture classification is a very primary focus of texture analysis. Like a lot of research has been taking place on texture classification and even like segmentation and synthesis, but like shape extraction has commonly been avoided in the research community. So now when you go and you classify the texture analysis methods, so these are how they are broadly classified into statistical methods, model-based methods, transforms-based methods, and structural methods. So what we do in statistical methods is we consider texture to be a quantitative measure of the pixel intensities in the ROI. And statistical calculations are performed on the intensity distribution functions of pixels. So this is useful for the spot localizations of pixels, and especially when the pixels are small. And some common approaches used here are histograms, co-occurrence matrices, local binary descriptors, GLCM. In model-based unit like methods, we consider the initial units like the pixel region, the shape, and the layout, which is the geometric relationships between these pixels. And the model of the image is then created to perform image synthesis. So this is suitable for textures with regular structures, but it's not optimal for textures which have irregular structures. And some common like model-based methods are AR models, are really popular autoregressive models, fractal models, Markov square theory, Gibbs, and hidden Markov model. In transform-based methods, the image gets transformed into another subspace. And this is done so that the texture is more easily distinguishable in the new space. And some common approaches employed here are spectral, Gabor, wavelet, curvelet transform. And in like structural methods, you consider texture to be a set of texels or a set of repeated relationships. You have well-defined structural elements over here, and some approaches are edge features and skeleton representations. So talking about the major tasks of texture analysis, as you can see in the image here, first you get the image and then you do some pre-processing, segmentation and labeling. You figure out what are your ROIs or your region of interest, and then you extract the features from there, you classify, and then you evaluate your results. So texture analysis is actually really useful in the medical imaging field, especially like with detection of breast cancer and in like mammographies. It's really helpful in reading x-ray scans. So like like how textures are, so based on that, so when we go on the major tasks of texture analysis, the key areas affecting texture analysis, they are pre-processing, feature extraction, and texture classification. So if you can see here in pre-processing difficulties, an example, here you have the sample circular region of interest, and then we apply some pre-processing techniques on that, like histogram equalization, and we receive this output. So pre-processing is actually useful to remove the noise and the distortion from the image to enhance the input image quality and for color space transformations. And some operations performed here are color to gray level conversions, interest area selections, and gray level normalizations. And some pre-processing algorithms used are the histogram equalization algorithm, which is a really famous one, the median filter MF algorithm, and the sharpening algorithm. So in histogram equalization, you work on small ROIs of like the interest regions called tiles. You automatically enhance the digital image, and the results from this technique are actually predictable most of the times. So contrast of each like ROI is enhanced, and the neighboring tiles are combined using bilinear interpolations to remove the boundaries. In median filter, you remove the noise from the image and signals, and here each pixel actually contains the median value of the neighboring pixels or the pixels in the neighborhood. And this method maintains the preservation of edges and boundaries. So that's really useful if our application wants to keep the edges during noise removal. And in sharpening, first you sharpen the region of interest or the image, and to do that, first you blur the image, and then your edges are detected in the blur region of interest, and that is used to produce a sharper image. Now talking about feature extraction, in the first like image, you can see that you are acquiring and doing some pre-processing techniques on that, and in the second photo, you are having your region of interest detected and your features extracted. Similarly, your texture analysis is used for breast cancer, as I said before, like based on the properties of texture, because we can easily distinguish them in like surfaces. They really help in medical imaging and fields like mammography, X-ray scans, MRIs. So this is where texture analysis is being used for breast cancer. And you first do the image pre-processing in A and then feature extraction in B. So talking about feature extraction, here you quantify the characteristics of the texture by locating the points that distinguish and separate them. And the extracted features have high influence on the classifier's accuracy. So this is used for texture discrimination and shape determination. Some really common datasets, widely known datasets used are MM98, GP94, and the Brodaz dataset. Now talking about like feature extraction algorithms, there are a lot of algorithms present, but I have like mentioned a few over here. Although there are many approaches that can be used, so I've mentioned the widely known ones over here. So when you do local binary pattern approach, here you label pixels of images by thresholding the neighborhood values with binary number results. The advantage is it has high classification accuracy and it's useful for grayscale images and it's computationally simple. But the limitation is that it has a slow recognition speed on large databases and it's really sensitive to noise. The next one is the SIFT approach. Here it detects the local features in the image. So it's a local method, it's a feature-based method, and it contains a feature detector and descriptor. So this is not like it can, it's not affected by invariance and changes in rotation, scale, and illumination, and it generates large number of features. So it has high accuracy in image stitching. But again, the limitation is that it has a slow recognition speed on large databases. So the next is GLCM, which was proposed by Heraldic, and this is also a really famous feature extraction approach. So yours, like you consider the statistical relationships between the adjacent pixels. So how often do pixel pair values interact with each other? And the advantage is that here the image compression time is really small, especially in converting like RGB to gray level images compared to the other techniques. And this can also be used for video estimation. But the limitation is that you need like a lot of computations, large number of matrices and pixels, and it's not invariant to real world properties that are found in textures like rotation or scale changes. And because like this method was proposed by Heraldic, and it always like has 14 texture features, which are the output. So that can oftentimes be redundant, especially with displacement vectors. Now going on to texture spectrum, here you consider sets of small essential units or texture units which characterize the local texture information in all the 8 directions. So here you characterize the texture spectrum instead of the features. And the advantage is that this is a computationally simple method. It's useful for feature extraction and even detecting the boundaries and the edges. And this can directly be used for image classification and analysis. But the limitation is the low result accuracy because of dependence on the texture spectrum. Now, if over here you can see, we want to perform texture classification. So these different images have or ROIs have been assigned to predetermined like label classes from A to H. And the ones we are concerned with are the ROIs marked in red. So texture classification, it decides what category an image belongs to or what label an image belongs to. So as we saw there, the ROIs we were concerned with were belonging to category C and H. And it takes the texture features, which are the training samples as the input, and it compares them with the testing samples to give the output. So the classification accuracy is the number of correct matches upon the total number of testing images. And there are two phases here, the learning phase and the recognition phase. So in the learning phase, the texture model content is built and all the texture features are extracted from the training samples. And we yield a set of textural like vector spaces feature sets with each image. And in the recognition phase, the texture content is described like using the yielding features, which are compared to the training samples, and then the output is obtained for the best match. And if we have false positives, they are rejected like through multiple layers of learning and recognition. And we also can penalize the model with a loss function. So now talking about the texture classification types, we have supervised texture classification and unsupervised texture classification. So in supervised texture classification, we don't need to have a prior knowledge of classes to employ the statistical like pattern classification techniques. The classes must be defined through the use of training textures. So the goal of the supervised stage is to take the existing information that we have for higher level analysis, and we can directly use annotated data sets or we can annotate them manually. So KNN, SVM, and ANN are some common supervised techniques of classification. And in unsupervised texture classification, we don't have a prior knowledge of like the classes. And the goal here is to automatically segregate the pixels into statistical routines, which are known as clustering. And here, like a common example of unsupervised texture classification is self-organizing maps, but SVMs are have shown to be more stable than SOMs for evaluating the texture features. So some common texture classification algorithms are KNN, ANN, and a support vector machine. There are many more, but I've just listed the most widely known ones. So KNN trains images and gets the nearest neighbors depending on the least distance. And to classify the new data, we used previously categorized data. So this is one of the simplest classifiers using supervised learning. And the advantage is easy implementation. It doesn't have a training period and it stores the training data set and learns while making the prediction. So it's much faster than other algorithms that require training like support vector machines. But the limitation is that it's sensitive to noise and missing data, and it has low accuracy with large data sets, and it also needs normalized data. ANNs actually are based on the human brain. So they connect, like they have a set of input output networks where weights are associated and with each like pair of input output networks, and we predict output based on the input images. And it's also known as feed-forward neural networks because inputs are associated in the forward direction. So it's capable of learning any nonlinear function, but the limitation is that 2D images are converted to 1D vectors. So that increases the number of trainable parameters. And support vector machines distinguish categories of objects, and it's really good for two-group classifications. So the advantage is the effectiveness in high dimensional spaces, especially if the number of dimensions are greater than the number of samples. And it's memory efficient and versatile, but the limitation is how it underperforms in large data sets, especially if the number of pixels of interest exceed the number of training samples. So here I've listed some common state-of-the-art texture analysis methods. I've done their comparison, and I've listed the author, the paper title, and here the method is listed as well. So local binary patterns, grade level co-occurrence matrices, and SVM, and even the data set that has been used. So these are some really famous ones, especially in texture recognition and analysis. And the classifier used in the accuracy is achieved. So we see that we got a really good accuracy with SVM and KNN, but we had a low accuracy with ANN. So talking about the conclusion and the future work. So because the texture definition is not known to the, there is no formal definition, the texture definition selected by the researcher strongly impacts the choice of texture analysis methods and classification techniques. And as the real world textures are not uniform, there are a lot of issues that occur like invariance, fine transformation, scaling, rotations, colors, then changes in scale, changes in size and magnitude. And many methods are rotation invariant, but only few are noise sensitive. So, things like facial recognition, ROI categorization, segmentation, defect detection, they all require analyzing small size images at fast speeds. So current methods are unable to achieve this. So what we need to tackle in the future is to improve the training sets, the computational efficiency for higher detection rates, and recognition accuracy with large data sets, because training is really time consuming. And the future work should definitely go beyond texture detection and classification. So more effort should be put into 3D texture analysis, developing semantic descriptive texture attributes, and studying the compositional structure of texture patterns. And so, yeah, that's it from me. Thank you so much. And I would really like to thank Professor Ying Wu for giving us this opportunity to research and find out so much about the fields of computer vision and statistical pattern recognition. I have definitely put more literature into my paper. So you would find more information related to this topic over there. Thank you so much.